Now, as we add energy to a substance, we're going to see it obviously get hotter and hotter, and eventually it's going to change phase, and we're going to go through a series of different phases as we continue to add or subtract energy from a system. And there are three main states of matter, four that we're really going to talk about in this class, and that's solids, liquids, gases, and plasmas. And most of the matter that we find on Earth is one of the first three phases, solid, liquid, or gas. But most of the matter in the universe is actually in the plasma state. And the reason for this is that plasma is a superheated gas, and it's what actually makes up stars. And since a huge majority of the mass in the universe is in stars, then most of the mass of the universe is in the plasma state. Now, if we look at each of these phases a little bit more closely, we can start by looking at some of the macroscopic characteristics, the things that we can see very clearly about each one. So, we'll start with solids. Solids have a definite shape. If you take a solid and you put it from container to container, the shape stays the same. It's a rigid structure. And it has a definite volume. So again, if we change it from container to container, that volume stays the same. And while you might be able to compress a solid a little bit, depending on what it is, for the most part, solids are incompressible. And compared to the other ones, they don't diffuse. So what that means is that the particles don't spread out into their environment, and the density compared to the other states is high. Then we get to liquids. Liquids, their shape is variable, and what that means is that they will take the shape of the container. And so if you have a beaker of water, the shape of the water is the shape of the beaker. If you then pour it into a sippy cup shaped like Elmo, the water is going to take on the shape of the sippy cup and look like Elmo. But even though the shape is going to change, the amount or volume of the water will stay the same. So even though we change containers, the volume of the liquid is not going to change. Liquids are a little more compressible than solids, but still not very much so. Liquids do diffuse, and you can see that if you take food coloring and you put a few drops of food coloring into water, and you can see how it kind of spreads throughout the water. That's what we're talking about. We're talking about diffusion. And then it still has a pretty high density. As we go from solids to liquids, the density doesn't change much. And then our third phase is the gas. And gases take the shape and the volume of their container. So whatever the size and shape of the container is, that's the size and shape of your sample of gas. And as part of that, they're very compressible. Okay, there's a lot of space in between those gas molecules, and so you can compress them into a very small container, or if you release them into a large container, they'll spread throughout to fill the room. They diffuse very, very fast. If you were to pop a balloon, the air that was in that balloon would spread out throughout the entire room very quickly. And again, this idea of an enormous amount of relative space in between the molecules means that it has a low density when compared to the other two phases. So those are macroscopic. Now if we look at the microscopic characteristics, the things that we can't see as easily, these are really just related to the energy associated with the particles. Solids have only vibrational energy. And the reason for this, and when something is a solid, that means that those intermolecular forces are very strong, and the molecules are held in a very rigid structure, and so they don't move around much. They do vibrate, though. They kind of oscillate back and forth. They vibrate back and forth, and so that's the only type of kinetic energy that they have. But there's a lot of potential energy based on their position in the field with the other molecules. As we add thermal energy to the system and we go from a solid to a liquid, the molecules now start to rotate a little bit, so they start to spin a little bit. Not only do they vibrate back and forth, but they also spin around an axis, kind of like the Earth spins around its axis. So we have vibrational, we have rotational, And also, those molecules can now flow around each other a little bit. So there's some translational as well. They can move around relative to the molecules around them. And we've also increased the amount of potential energy due to their position. And then the third phase, gases, the majority of the kinetic energy is actually translational. These molecules are flying all over the place very, very quickly. They have a lot of translational motion, or a lot of translational energy, but then their rotational and vibrational motions have also increased, although the one that's increased the most is the translational. So they're spinning a little bit faster, they're still vibrating back and forth, but now they're flying around their container much more quickly. And then again, we have greater distances between the molecules. We have a much larger potential energy associated with those molecules. Okay, now let's look at each individual phase a little bit more closely in terms of the arrangement of the particles. So solids, those particles are very, very closely packed, and the intermolecular forces between each molecule and its neighbor are very strong, and so that's why there's only a little bit of that vibrational motion. There's not any rotational, and there's certainly not any translational. Those molecules are held in very, very rigid positions. And the reason that they have that potential energy is because of the forces of attraction between the molecules. Okay, so think ice, think bricks, things like that. Those structures are very solid, very rigid. When we get to liquids, they're still very closely packed, okay? Which is why they have a definite volume, but even though the bonding is strong, it's looser than it was with solids. And so now the molecules have a little bit more freedom. Now they can start to rotate a little bit. Now they can start to kind of move around each other. And what ends up happening is those intermolecular forces, those intermolecular bonds, are actually breaking and reforming, and it's this continual process as the molecules move around each other. Those intermolecular forces form bonds, they break, they form, they reform, they break, they reform as the molecules move around. And here, because now the distance between the individual molecules has increased, the potential energy between the molecules, because of the intermolecular forces, is also increased. It's like if you take a ball and you lift it 2 feet above the earth, it has some gravitational energy. If you lift it higher above the earth, now its gravitational potential energy is increased. We have the same thing occurring between the molecules. And then finally we have gases, and in our gases there's an enormous amount of space between the molecules relative to solids and liquids. And the only interactions between the molecules are when they come very, very close together, or occasionally when they collide. And at that point now there's some interaction. The intermolecular forces try and pull them back together, but generally they have too much kinetic energy, and so they might slow down. They still kind of go flying past each other, or they rebound off of each other. And because there's such a great distance in between each individual molecule, the potential energy here is much greater than the other two phases of matter.